I welcome you all to 31st lecture of this course. Now, I've already discussed one of the most popular non-traditional tools for optimization, that is genetic algorithm. Now, today I'm just going to start discussing the principle of some other non-traditional optimization tools like simulated annealing and particle swarm optimization, PSO. Now, remember one thing, each of these tools is having its own merits and demerits. Okay. Now, the merits and demerits of genetic algorithm we have already discussed. Okay. And let us start with discussing some other popular non-traditional tools for optimization. But do not think that these particular tools are having only merits and no demerits. It's not like that. Okay. Now, I'm going to start with a very popular non-traditional tool for optimization, that is simulated annealing. And remember, this particular tool, it was proposed long back in the year 1953, well before the introduction of genetic algorithms. Okay, genetic algorithms was introduced in the year 1965, but this simulated annealing came in the year 1953. Okay, now let us see the working principle of this simulated annealing, and in short, this is known as SA, simulated annealing, SA. Now, this concept was proposed by Metropolis, others, the and 53. Now, here in simulated annealing, we try to model the cooling process of molten metal in the artificial way. And this particular cooling process of molten metal is modeled artificially to develop or design an optimization tool called simulated annealing. Now, whenever a metal is in molten state, its energy state is very high. It is at the highest energy state. The molten metal is its highest energy state. And if it is allowed to solidify, we will be getting the solid metal. And whenever the metal is in solid state, it has got the lowest energy. Okay. So starting from the molten metal, if you allow it to cool down, then at the end I will be getting the solid metal. That means from the highest energy level, it will move towards the lowest energy level during the cooling process. Okay. And this particular, the fact has been modeled artificially to solve the minimization problem. Okay, I can also solve the maximization problem, but the energy state is going to be reduced starting from its highest level to the lowest level. So on principle, actually, we are solving the minimization problem. Okay, now let us see how does it work. Now, exactly the same thing, whatever I stated, I'm showing it here with the help of this schematic view. The molten metal is at highest energy state. You allow it to solidify, there will be cooling, then it will reach its solid state, and solid state corresponds to the minimum energy state. Okay, so the highest energy state to the lowest energy state through this particular the cooling process. Now remember, the metallurgical property of this particular metal and its mechanical properties are too much dependent on the cooling rate, the rate of cooling. Okay. The cooling rate is going to control the crystallized structure, okay, and it is going to control the metallurgical properties and mechanical properties of this particular the metal. Okay, now let us see what happens if I allow a very high cooling rate or if I allow a slow cooling rate that I'm going to study. Supposing that we have got the molten metal, say molten steel sort of thing, okay, and I want to solidify to get the solid state. Now, if I allow the high cooling rate, what will happen? The molten metal will be converted into its polycrystalline state. So you may not get a single crystal. Instead, you'll be getting different types of crystals. And crystals could be of different types. So if I consider the high cooling rate, there is a possibility you'll be getting the polycrystalline state of that particular metal after solidification. Okay. On the other hand, if I just go for the slow cooling rate, there is a possibility that I'll be getting a single crystal of that particular the metal. Okay, there will be a crystal of only one type, that is called a single crystal or crystalline state. Okay, so let me repeat, if I go for high cooling rate, you'll be getting the polycrystalline state. If I go for slow cooling rate, it will be getting the crystalline state belonging to only one single crystal. Okay. Now, there is a difference in properties between the polycrystalline state and your single crystalline state. Now, whenever the metal is in a single crystal state or a crystalline state, it will be having the lowest level of energy. Okay, now let me repeat. If you get polycrystalline state and if you get on the other hand crystalline state, the crystalline state will have energy. Okay, and that is why we generally go for the method of slow cooling if you want to get a single crystal in the solidified state. And I hope some of you have studied in physical metallurgy. Okay, the method of slow cooling is known as the annealing. Okay, so annealing is a process which is nothing but the method of slow cooling. Okay, so we are going for the slow cooling so that we can get the crystalline state of the metal, because crystalline state corresponds to the minimum level of energy of that particular the metal. Okay, so in this particular optimization tool, I'm just going to model artificially the slow cooling of molten metal, say steel. Okay. Now let us see how to do it. How does it work? Now to discuss the working principle of this particular simulated annealing, let me try to take one problem, very simple problem sort of thing. Our aim is to minimize y. Y is a function of capital X. What is capital X? Capital X is a collection of some design variables, small x1, x2 up to xn. And X is lying between X minimum and X maximum. So this is the objective function. This is your, if you remember, this is the variable bound. Okay. And for simplicity, I did not consider any functional constraint here. Okay. Now let us see how does it work. Now step 1, we assume initial high temperature of molten metal, say T naught, and select an initial solution X naught at random. Okay. So the starting temperature of the molten metal T naught and the initial solution capital X naught we'll have to assume at random. Step 1. Please stop your audio and video. Now there must be one termination criteria, okay? Otherwise, you cannot stop that particular algorithm in the computer program, okay? That particular termination criterion is denoted by epsilon, and epsilon has got a small numerical value. I'll be discussing, okay? Actually, what we do, for each of the iteration, we try to find out what is the level of energy, and we try to calculate what is the difference in energy. Okay. Now, this particular difference in energy has to be less than equals to this epsilon, that small value. Then only we declare that your algorithm has reached that particular level. Okay. And it is able to indicate the optimized solution. Okay. I'll be discussing this in much more details after some time. Set iteration number t is equals to 0. Step 2. Calculate the temperature of t plus 1 iteration. As I told that the initial iteration, the first iteration, we assume the values for the variables and the initial temperature of the molten metal at random. Okay. Now we'll have to go for the second iteration. Now in the second iteration, what I am going to do is, we are going to reduce the temperature, because this is a cooling process, and due to this cooling process, the temperature of the molten metal is going to be reduced. Okay. And what we do, we try to reduce the temperature to 50%, okay, in the next iteration. I can also reduce to 40%, 60%. Okay. Accordingly, you will be getting that particular the sharp speed. Okay. But let me assume that we reduce the temperature to 50%. That is your capital T at t plus 1 iteration is nothing but 0.5 multiplied by capital T at T8 iteration. Capital T indicates the temperature and small t denotes the iteration, number of iteration. Okay. So you reduce the temperature to 50% and generate a candidate solution for I plus 1, t plus 1 iteration, that is x t plus 1, once again at random in the neighborhood of xt, using the random number generator in the computer program. Okay. So the solution for the next iteration, that is the second iteration, that is xt plus 1, are generated at random in the neighborhood of xt, that is the previous solution, okay, using the random number generator. And once you've generated the probable solution for the next iteration, now we'll have to check whether it could be accepted or not. Okay. How to check it? Now to check it, actually what we do is, we try to find out how much is the change in energy from first iteration to second iteration. How much is the change in energy? Okay. So the change in energy, that is delta E, is nothing but energy corresponding to capital X at t plus 1th iteration minus energy corresponding to capital X at tth iteration. Okay. And it has to be less than 0. Okay. If it is found to be less than 0, that means what? That means your energy at t plus 1th iteration is less than the energy at tth iteration, and this is a minimization problem. So xt plus 1 is a good solution. So we can accept xt plus 1 as the next iteration, and we set t equals to t plus 1. So I'm increasing the iteration number because this particular solution, candidate solution, has been accepted. Okay. So I think I'm clear to all of you. Now, there is another possibility that this particular solution xt plus 1 generated at random in the neighborhood of xt, it may not be accepted. That means your this particular condition may not hold good. Okay. So if it does not hold good, then also we want to give a chance to the solution, okay, to be considered if it follows this particular the condition. What is this particular condition? That I'm going to discuss in details. Okay. So what is that particular rule? Else generate a random number r lying in the range of 0 to 1, and if r is found to be less than equals to e raised to the power minus delta e divided by capital T corresponding to t plus 1. Okay. So if this particular condition holds good, although it is not a good solution, we accept for the time being. Okay, are you getting my point? Now, what is the reason behind this particular expression? That I'm going to discuss after 2-3 slides. So you'll have to wait a little bit. Once again, I'll be coming back to this. Okay, let me repeat. We generate a random number r, and if it is found to be less than equals to e raised to the power minus delta e divided by t corresponding to t plus 1, we give a chance, although this is not a good solution, but we accept it. Why do you do? The reason I have already told you. Okay, that at the level of assistant professor, a candidate may not be a very good in teaching and research and administration. Okay, but what he do is, even if he is not found to be very good, we accept as a faculty member at the lowest level, that is assistant professor, and we give a chance to him or her to grow in career. Okay, if he or she can grow in career, then he will be rewarded at the end. So we want to give a chance even if he is not the best. Okay, we just want to give a chance to the candidate at the lowest level, that is at the level of assistant professor, while selecting faculty for an institute. Okay, now if he and she can improve his career or her career, there is a possibility that he will be getting the next promotion like associate professor, full professor, HAG professor, and all such things. Okay, and if he cannot, then he will remain as assistant professor throughout his career, and he or she will have to retire as assistant professor. Okay, so exactly the same principle is followed here. We give a chance to the solution, even if it is not found to be the best, to excel, to improve his or her career. Okay, and let us see what happens in future. Okay, now if this particular condition does not hold good, else we reject xt plus 1 and set t equals to t and go to step 2. Okay, so this is the way actually we accept or reject the solutions in simulated annealing. Okay, now step 4, if the mode value of the difference between the two energy state, that is your ext plus 1 minus ext, if it becomes less than epsilon, the termination criteria having a small numerical value, and please remember that t reaches a small value, we terminate the program. Okay, now during the solidification or the cooling, the molten metal initially will have a very high temperature. Sorry, could be around say 3000 or 3500 degree Kelvin, say. Okay, Now, gradually the temperature will go on decreasing. The moment it becomes equal to the atmospheric temperature, then only you will be getting the solidified steel. Okay, so we'll have to wait up to the atmospheric temperature. Are you getting my point? So T should reach a small value. Okay, and if this particular condition holds good, we terminate the program. Okay, so this is the termination criteria. Now I'm just going to discuss the reason behind that particular expression, that is e raised to the power minus delta E divided by T. So this particular expression. Okay, so I'm just going to discuss why is it like this. Okay. Now to discuss this, I'll have to enter a little bit on thermodynamics. All of you have studied thermodynamics. Okay. So I'll have to go for the Boltzmann probability distribution, which all of you have studied in the course on thermodynamics. Okay. Now, according to Boltzmann probability distribution, a system kept in thermal equilibrium at temperature T has its energy distributed probabilistically as PE, that is the probability of energy distribution, is exponential minus E divided by KT. What is E? E is nothing but the energy state. K is the Boltzmann constant, and capital T is nothing but the temperature in degree Kelvin. I think all of you have studied in thermodynamics, Boltzmann probability distribution. Now it is very simple. Any thermal system at temperature T, if it is in equilibrium, then its energy will be probabilistically distributed as PE equals to exponential minus E divided by KT. Okay, and here for simplicity, we have considered that K is equal to 1. But truly speaking, K is not equal to 1. K has got a numerical value. You can just go for the Google search. You'll be getting approximately, I can remember, 6 point something into 10 raised to the power such a huge number is the Boltzmann constant. Okay, so you can find out the exact value from the Google search. Okay, now here we use K is equals to 1. Okay. Now why is it so? Why do you consider that this particular your distribution? Let us try to understand. Now, as I told that we are going to model the cooling process of molten metal through a large number of iterations. So initially the temperature was the highest one, and at the end I'll be getting the lowest temperature through a large number of iterations. So as iteration proceeds, that means as small t increases, what will happen to the capital T, that is the temperature? The temperature is going to be reduced. Okay, as I told, we go for 50% reduction in the next, once again 50% reduction in the next, and so on. So what will happen to capital T? The capital T is going to be reduced. Okay, what will now K is 1. So what will happen to E divided by capital T? Capital T is going to be reduced. So E by T is going to increase. Okay, but there is one negative sign here. That means 1 divided by E raised to the power E by KT, and E by T is going to increase. So what will happen to the probability? Probability is going to be reduced. Okay, and what is this probability? This probability stands for the probability of selecting the bad solution. So initially at high temperature, at early iteration, the probability of selecting bad solution is more. As temperature decreases, as iteration proceeds, the probability of selecting the bad solution is less. At the assistant professor level, there is a probability of being selected the bad solution, high probability. But as iteration proceeds at the level of associate and full professor and HAG professor, okay, not all candidates are going to get that promotion. Okay, the probability of selecting the bad solution should be less. Are you getting my point? So this is the physical significance of your this Boltzmann probability distribution. And if you see on a plot with the iteration, the probability of energy distribution is going to be reduced. You can have a look. Okay. And that is why in simulated annealing, Metropolis et al., they use the concept of your this Boltzmann probability distribution. Okay, so I hope I am clear to all of you. Okay, so this is the way actually your this simulated annealing works, and it has got one very big advantage, one big merit I should say, that is its mathematical convergence proof. As it is copying the cooling process of a molten metal, its metallurgy is known to us, and with the help of some mathematical models like probability distribution, Boltzmann probability distribution, and others, so mathematically its convergence could be proved. Okay, so this particular algorithm is having the concrete mathematical convergence proof, which is which we do not have for other algorithms till now, like genetic algorithms, PSO, and others. But this particular simulated annealing has got the concrete mathematical convergence proof. Okay, so I think I'm clear to all of you. Now I'm just going to solve one numerical example just to explain the working principle of this particular the simulated annealing. Okay, and as I told, on principle, it can solve the minimization problem. It solves the energy minimization problem. Okay, so minimize y is a function of uh, capital X. Capital X is a collection of two variables, small x1 and x2. And supposing that this is equals to x1 plus x2 minus x1 square minus x2 square. So this is actually the objective function, and these are the variable bounds. Small x1, x2 are lying between 0 and 5. Okay, and I'm just going to read it out, the statement of this particular problem. Assume the initial temperature of molten metal T naught is equal to 3000 degree Kelvin. Initial random solution X naught, say 2.5 and 2.5, lying within 0 and 5. Termination criteria epsilon 0.001. Let us assume that the random numbers varying in the range of 0 to 1 are as follows. So just to carry out the hand calculation, so I took the help of a few random numbers like 0.3, 0.8, 0.7, 0.6, and so on. Okay, to carry out that particular calculation in the iteration. So the initial temperature that is assumed to 3000 degree Kelvin, and initial solution that is 2.5, 2.5, which are generated at random. Now corresponding to small x1 equals to 2.5 and small x2 equals to 2.5, I can calculate the value of the objective function. Okay, so using the expression of objective function, you can find out what is Ex naught. Okay, you simply substitute the values for small x1, x2, and you'll be getting minus 7.5. So Ex naught is minus 7.5. Okay. Now we go for iteration 1. So this is the initial iteration. Now iteration 1 is basically iteration 2 we can call. Here the temperature is reduced to 50%. So T1 is 50% of T naught. That is nothing but 1500 degree Kelvin, and corresponding to the random numbers 0.3 and 0.8, you can see that we assume those random numbers for the hand calculation. Okay, 0.3 and 0.8. Now all such random numbers in the computer program that will be generated using random number generator. There are several random number generators in C programming. Okay, so you can rand is one, and there are some others. So you can use those random number generator. Okay, now corresponding to the random numbers 0.3. How to find out the real value? It is very simple. So corresponding to the 0.3, if you remember the way we calculated in the last class, okay, and the class before last, that x is nothing but n into x max minus x minimum plus x minimum. Follow the same principle. Because here we know the range for x1 and x2 is 0 to 5. 0 to 5. So what is the range? Range is 5, 5.0. So 5.0 multiplied by 0.3 is 1.5, and the minimum value is 0. So 0 plus 1.5 is 1.5. Similarly, corresponding to 0.8, you can find out this is equals to 4.0. That is 0.8 multiplied by 5.0 minus 0.0. That is nothing but 4.0. Okay. So corresponding to the random numbers 0.3 and 0.8, we can get x1 is nothing but 1.5 and 4.0. Now, corresponding to this 1.5 and 4.0, I can find out the value of the objective function, and the value of the objective function is nothing but is your EX1, that is 12.75. Okay, so you can find out the energy corresponding to this particular, the X1. Now, how much was X0? X0 was minus 7.5, and X1, EX1 is 12.75. So EX1 is less than EX0. So we select X1 as the next point. Okay, because it is going to follow that particular condition that EX1 is less than EX0. This is a minimization problem. So we select X1 as the next solution. Okay. And we try to find out what is the change in energy. So the change in energy is denoted by delta E. Okay. And this particular delta E is greater than epsilon. Epsilon is a small value. So algorithm has not reached that optimal solution. So we will have to go to the next iteration. So we are going for the next iteration. Okay, because delta E is found to be much higher compared to the value of epsilon, which is the termination criteria. Okay, so still the metal is in molten state. It has not reached that particular your solid state. So we go for the next iteration. Next iteration, once again, we reduce the temperature to 50%. So T2 is equals to 50% of T1, that is 750 degree Kelvin, and corresponding to the random number 0.7 and 0.6, okay, which you have already stated in the statement of the problem. Okay, we get X2, that is a collection of small x1, x2 is nothing but 0.7 multiplied by 5.0. So this is 3.5 and this is equals to 3.0. Okay. So this is the way we calculate the next probable solution, that is capital X2, and corresponding to capital X2 we try to calculate the energy. So energy corresponding to X2 is nothing but minus 14.75. Okay, this is the value of the objective function corresponding to your X2. As Ex2 is found to be less than Ex1, okay, we select X2 as the next point. Okay, so this particular condition holds good. So X2 is considered also as the next point. And the change in energy, that is delta E, is nothing but the mod of the difference between energy corresponding to X2 and energy corresponding to X1, that is equals to 2.0. And once again, delta E is found to be much higher compared to the termination criteria epsilon. So we go to the next iteration. Okay. So next iteration, T3 is 50% of T2, that is 375 degree Kelvin, corresponding to the random numbers 0.2 and 0.5. We get X3 equals to how much? 0.2 multiplied by 5.0, that is 1.0, and 0.5 multiplied by 5.0, that is 2.5. So we get X3 like this. Okay, we calculate the objective function value corresponding to X3. So Ex3 is minus 3.75. Now here Ex3 is found to be greater than Ex2. So it does not hold good. Okay, because this is a minimization problem. So typically for this minimization problem, Ex3 should have been less than Ex2, but it is just the reverse. Ex3 is found to be greater than Ex2. So we cannot select X3 as the next point. But as I told, we want to give a chance, okay, to this particular solution with the help of that Boltzmann probability distribution, that particular the concept. Now, how to implement? I have already discussed. The next random number is found to be 0.6, as I have already stated in the statement of the problem. Now, change in energy, that is delta E, is nothing but the mod value of Ex3 minus Ex2, that is equal to 11.0. And we try to calculate exponential. If you remember, R equals to uh, R less than equals to this particular expression. Okay, so I'm just going to calculate exponential minus delta E by T3. So minus delta E by T3, its exponential is found to be 0.97. Okay, now this particular R is found to be less than 0.97. So we accept X3 as the next point. Okay, because according to this particular condition, so we are in a position to accept X3 as the next point, although it failed that particular, the first condition. Now the above procedure is repeated till it reaches the termination criteria. So this process will go on and go on and go on, and ultimately you will be getting that particular optimal solution. Okay. Now this is the way actually your simulated annealing works. Okay. And it could reach very good popularity. Okay. In fact, before the genetic algorithm, and uh, might be around say 1970-71. Okay, simulated annealing also reached too much popularity. Okay, then 65 genetic algorithm came. What people came to know about around 75. Okay, because for the first 10 years, it was within their own research group of Professor John Holland and his PhD students like David Goldberg and others. Okay. Then around 75, other people came to know about this particular genetic algorithm. But this, your simulated annealing, that was popular uh, among the researcher as a non-traditional optimization tool. I hope the principle of simulated annealing is clear to all of you. Okay. Now, if there is any doubt, we'll be discussing if there is any doubt on simulated annealing before I start with another very efficient tool, but still it has got some demerits, that is vertical swarm optimization, PSO. So if you have any doubt regarding the simulated annealing, you are free to ask me, and then we are going to start with the vertical swarm optimization. Yes, if there is any doubt, you can ask me now.
Hello, sir. Sir, am I audible?
Yes, tell me.
Yes, sir. Sir, I just wanted to know about the polycrystalline, the formation of polycrystalline state. Is it analogous to the preliminary convergence that we had in genetic algorithms, like
Actually,
the premature convergence?
if it is polycrystalline state, then you that it is not going to reach its lowest energy level. Are you getting my point? So the optimal solution which you are getting, it is some sort of premature solution. You are right. Okay. So we'll have to go for the method of slow cooling. You see, high cooling means what? The rate of change is very high. Cooling rate is high. There is a possibility you'll be getting some optimal solution, but that may not be the true optimal. As I told, that premature conversion, I'm declaring I'm the best in the world, but it is may not be the true. But I'm thinking I'm the best in the world. Okay, that is actually the example of premature conversion. Okay, there is no end of learning. Okay, nobody should declare I'm the best in the world. Okay, that is a clear indication of premature conversion. Same is true here. The genetic algorithm is going to face that particular problem. Simulated annealing is also going to face that particular problem. Okay. There is a saying, no, slow and steady wins the game. Okay. So you'll have to be slow and steady. The algorithm has to be slow and steady. Okay. It should not be too fast. It should not be too like slow. It has to be slow and steady. Then only it will win. Okay. The algorithm is going to win at the end. Okay. And the chance of premature convergence will be less. Are you getting my point?
Yes, sir. And it will be determined by the rate at which we will reduce it. For example, in this case, we had considered 0.5.
Huh.
And if we are to increase that, then there might be a possibility of the polycrystalline formation. And if we decrease it, there will be more time to converge
Yes.
to the.
Yes. Like
Yes.
if you just go for more reduction, okay, that means we are going for fast cooling rate. Okay, fast cooling rate, very quickly you'll be getting some solution. And you thought that I have reached, but truly speaking, it is not true. Okay, so the cooling rate has to be slow. Okay, annealing means slow cooling. By annealing, in physical metallurgy, we mean a method of slow cooling is the annealing. Now, you might have heard about anneal steel. Anneal steel means what? The molten steel follow the method of slow cooling. Okay, get it solidified. That is the anneal steel. That's the process of annealing. Generally, we use anneal steel. Okay.
Yes, sir.
Hmm.
Yes, sir. Okay. Thank you, sir.
Okay, fine. Any other query? Any other query? Okay. If there is no other query, then we are going to start with another very popular non-traditional optimization tool. But once again, let me tell you that this particular PSO is not foolproof. There are some merits and demerits also. Okay. And I'm just going to mention what is the merit of this particular algorithm and what could be the demerit. Okay. And I'll also tell you to overcome that how we are thinking about intelligent optimization tool. And as I told several times that uh, one of your TAs, Amit Kumar Das, along with us, so he has developed another intelligent optimization tool like Bonobo Optimizer. Okay, that could be even better compared to your PSO. Okay, but I'll not be discussing the principle of Bonobo optimization tool here. I'll stop after discussing the particle swarm optimization. Okay, and if you're really interested, I have already sent to your, I think all the faculty members of mechanical, our code developed by Amit for the Bonobo optimizer. Okay, and the papers also. Okay. Now, this particle swarm optimization, it was proposed in the year 1995. But as I told, that getting literature at that time, it was very difficult. Okay. And although it was proposed in the year 1995, I could come to know after 5 years. So in 2000, I was visiting Kyushu University, Japan. That time I heard about this particular algorithm. But as I told, nowadays you people are getting literature very easily. Uh, our our time was very tough. We didn't get proper literature also. Even IIT Kanpur, we did not have the sufficient literature in the field of this optimization, subcompany, all such things. Okay, I remember I had to go to Statistical Institute, Indian Statistical Institute, Kolkata, and I'll have to go to their library to find out a few papers. I still remember. Okay. Anyway, so forget about that. So I came to know about this particular algorithm in 2000. Okay. And here the method which has been followed is very interesting. All of you have seen all such physical the problem. For example, say all of you might have seen the way pigeons fly in the sky. Huh? A large number of pigeons, okay, together they fly in the sky, but they do not collide with each other. Okay, so knowingly or unknowingly, they follow some principle of optimization. Another example, some of you might have aquarium at home, and in the aquarium, you'll find there are so many such pieces, and those pieces are swimming or moving in a group, but they are not colliding with each other. So knowingly or unknowingly, they are also following some principle of optimization. That particular principle is a vertical swarm optimization. Okay, it is a swarm of particles, group of solutions, group of individuals. Okay, although this is called vertical swarm optimization, it is actually a swarm of particles and they are optimizing. Are you getting my point? Swarm is nothing but a group. So group of particles, a group of solutions. Okay. Now it was proposed by Kennedy and Everhart in the year 1995. Once again, this is a population-based evolutionary computation technique. And as I told, it is developed based on simulating the bird flocking or fish schooling in the aquarium. Okay. The algorithm starts with a population, that is swarm of random solutions or the particles, and you'll see that these particles will change their velocity and position, okay, iteratively to reach that particular the globally optimal solution. Now here there is one plus point. The particles have memory and each of them keeps track of its previous local based position. This is very important, and that is actually the weak point of genetic algorithm. The solutions of genetic algorithm do not have memory, okay, but here in particle swarm optimization sorry, the particles or the solutions have memory, okay, and each of them keep track of its previous position, and that particular position is nothing but the p base. I'll be taking a very simple example, very practical example, uh, the concept of p base, and there is another thing that is called the g base. The particle with the greatest fitness is known as the global best PG of the swarm. What is this P best and global best? Let me take a very simple example. Okay. Now, supposing that Professor X wants to excel in his career. Okay. So, what should be the method? Professor X, at the end of each year, should review his or her performance. And he should compare his performance in the current year with that of the previous year, okay, with that of the previous year, and so on, okay, and go on updating the present best, the personal best. Are you getting my point? So Professor X wants to excel, and what he or she will have to do, he or she will have to compare his current best solution with the previous best, previous to previous best, and go on improving. Okay, this is one. At the same time, he'll have to find out who other people are working in the similar field in the whole world. Are you getting my point? And his performance has to be compared with the performance of other researchers working in the same area. And he'll have to find out what is the global best. Okay, so if I'm happy only with myself, I'm not doing my job. I'll have to see what others are doing in the same field of research and what is the global best and how to reach that global best. Are you getting my point? So I'll have to find out the global best by comparing the performances of all researchers, all professors working in that particular field of research. Okay, so there are two things. One is the personal best, another is your the global best. And I love to use the information of both personal best as well as global best if I want to excel, if I want to reach a particular level. Okay, the same thing has been copied in vertical swarm optimization. Okay, how to do it? I'm just going to discuss. Now here, the ith particle in d-dimension space is denoted by xi. This is a population-based approach. A particular solution is ith solution, that is denoted by capital Xi. And capital Xi consists of how many numerical values? Small d number of numerical values. xi1, xi2 up to xid. I varies from 1 to up to capital N. Capital N is the swarm size or the population size. In PSO, we call it swarm size. Okay. Now, P based of ith particle, once again, we'll have how many numerical values? small d number of numerical values. So P base of ith particle, that is denoted by Pi, and it has got small d information, that is Pi1, Pi2 up to Pid. Then comes global base is represented as Pg, that is nothing but the collection of Pg1, Pg2 up to Pgd. Okay, so d number of numerical values. Now the velocity of ith particle, once again it will have d dimension. So capital Vi is nothing but a collection of small vi1, small vi2, the last is small vid. Now the velocity and position of ith particle are updated. See, if you want to update the position, the first thing you'll have to do is you'll have to update the velocity, because position is nothing but velocity multiplied by time. S equals to Vt, all of you know. So we'll have to update the velocity, and if you can update the velocity iteratively, then you'll be able to update the position. Now let us see how to do it. Now this Vid, that is the velocity of ith particle, and I'm concentrating on dth dimension corresponding to t plus 1th iteration, is nothing but w multiplied by Vid corresponding to t plus C1 R1 PID minus XIDT plus C2 R2 PGD minus XIDT. Okay, I'm just going to explain each of these particular the terms. So our aim is to update the velocity of ith particle, and I'm concentrating on the dth dimension and its condition at t plus 1th iteration. That is nothing but w multiplied by the velocity in the previous iteration, the tth iteration. W is nothing but the inertia weight. Okay, inertia weight. So W into Vidt, that provides the initial momentum. If you remember in the last class, I told after the conclusion of the syllabus of soft computing that I could give some sort of initial momentum. Are you getting my point? I hope you remember that statement. This is the initial momentum. Okay. Now, if I give the initial momentum, and if you do not do anything after that, what will happen? Things will decay. So you are not going to improve your own condition. Are you getting my point? Although I have given you the initial momentum here, WVID is my responsibility as a teacher to give you. Okay. After that, whether you'll improve yourself or not, that depends on these two parameters, these two factors. What are those? The second thing is nothing but the cognitive component representing personal thinking. If I do not want to improve myself, who can help me in the world? Nobody. Even God cannot help you if you do not want to improve yourself. Are you getting my point? Now this C1 R1 into PID minus XIDT. This is what? This is the cognitive component. Cognitive component means you'll have to use your brain. You'll have to think. You'll have to think your position. You'll have to think how to improve my own position. Of course, in terms of knowledge. Okay. In terms of knowledge, how can I improve further? If I do not think, if I do not want to improve, if I have got no thinking, nobody can help you. It's a lost case. Okay. So what you'll have to do, you'll have to think on your capability, how to improve yourself. Okay. And lot of thinking has to be there in your brain. That is nothing but the cognitive component. Okay. There is another thing. Now let me tell you what are the components there in cognitive part. C1R1 multiplied by PID minus XIDT. C1 is what? A constant supplied by the user. Okay, that is called the cognitive constant. R1 is a random number lying between 0 and 1. PID minus XID. What is PID? Is the personal best. Each year, at the end of each year, I'll try to find out my best performance. I'll compare with the previous year and I'll upgrade it. That is my personal best. Okay. Now this PID minus XIDT, what happens to the variable position of that particle at tth iteration, previous iteration, plus C2R2 into PGD minus XIDT. That is nothing but the social component. Now it indicates the collaborating effect. It pulls the particles towards a globally particle found so far. Okay. That means if you want to improve yourself, you'll have to see what others are doing working in the same field. And you'll have to compare yourself. If you are making a mistake, you'll have to correct yourself. Okay. So that you can move in the right direction. So the social component you cannot ignore. You cannot declare I am the best in the world. I am not going to listen to anybody. What I think is the best. It cannot be like this. Okay, so you'll have to think about others. You'll have to give due weightage to others' thinking, and you'll have to update yourself according. Okay, that is actually your social component. That is C2R2 multiplied by PGD minus XIDT. What is PGD? PGD is nothing but the globally best. C2 is the social component constant. R2 is nothing but the random number. So C2R2 multiplied by PGD minus XIDT is the social component. Are you getting my point? So initial momentum, cognitive component, and social component, if all the three things are active, then only you can improve. Otherwise, there is no chance. Okay. So be careful about that. So whatever I'm teaching, if you just stop there, everything will go to the waste. So gradually this will decay. With time, you'll also forget the things. Okay. And all my effort will go to the wastage. Are you getting my point? So initial momentum I am providing. Now these two things you'll have to cultivate. Then only things will move in the proper direction. So this VID at t plus 1th iteration is actually the updated velocity in the next iteration. Okay. And once I've got the updated velocity, very easily I can update the position. That is XID at t plus 1th iteration is nothing but XID plus VID t plus 1 multiplied by time. So here time is nothing but the number of iterations. So each iteration, I'm just going to add 1. So here it is multiplied by 1. So this is the way we can update the velocity and position. All such things, whatever I told, I have written it here. Okay. So this is the way actually the PSO is working. Okay. So PSO is very simple. Okay. In fact, all the non-traditional tools for optimization, if you see the working principle, it is not difficult to understand. Okay. Now we start with an initial population of particles with random positions and velocity. We evaluate the fitness of the particle. Compare each particle's fitness with that of the current best to obtain the P best, the personal best. And once you've got P best for the whole swarm, now we can compare, find out what is the globally best. Update the velocity and position. Check whether it has reached the termination criterion. If it is yes, that is the end of the program. If it is no, you repeat this particular iteration. It is a very simple algorithm. Okay. Now, if I compare PSO with genetic algorithm, you'll understand the merits of this PSO compared to the genetic algorithm. Okay. PSO is a population-based search. Genetic algorithm is also a population-based search. In genetic algorithm, we have got the operators like crossover mutation, but in PSO, there is no such operator like crossover and mutation, and consequently, PSO is faster than genetic algorithm. Now, as I told, the genetic algorithm solutions do not have memory, but PSO particles have memory. Okay, once again, I'll be coming back to that after some time. Okay. Now, as it has got the memory, so PSO can carry out both the global as well as local search simultaneously. You know the meaning of global search and local search, and simultaneously it can carry out both the local as well as global search. On the other hand, genetic algorithm is a full tool for global optimization, but its local search capability is poor because it does not have the memory. Okay. And as I told, PSO is faster and genetic algorithm is slower. Okay. Now, PSO is expected to provide the better results compared to the GA for most of the optimization problems. Okay. That we have checked. We have solved many such optimization problems. And particularly for a complex objective function, we have seen for most of the problems, the PSO is found to be better compared to that of genetic algorithm. Okay. Now I'm just going to solve one numerical example. Okay. So maximize y equals to fx minus x square plus 5x plus 20. All of you know its solution. Very simple. You can use the calculus method. Okay. So find out dy dx, put equals to 0, solve for x. So you will be getting minus 2x plus 5 equals to 0. So x equals to 2.5. The solution is 2.5. Okay. And x will vary from minus 10 to plus 10. Now, if you want to solve it using PSO, let us see how does it work. So, very purposefully, actually, I designed this numerical example to show you at least one iteration of this particular the PSO. Iteration t equals to 0. Let us consider 10 initial solutions selected at random, lying within their respective, lying within the range of minus 10 to plus 10. Okay. And these solutions, 10 solutions are selected at random. Now x10 is minus 8.0, lying between this minus 10 and plus 10. x20 is 7.5, x30 is 6.0, x40 is minus 6.5, x50 is 9.0. Similarly, all such 10 solutions lying within this particular range, we have selected at random. So those are selected by me at random for the hand calculation. Okay. Now, once you've got, now this 0 corresponds to 0th iteration. First solution, first particle, second particle, there are 10 particles. Now, for each of the 10 particles, its velocity and position are to be updated, iterated. That is the problem. Now, once you've got the values for x, can we not find out the values for y? Using this expression of objective function, you can find out the values of the objective function, that is y1, y2, y3 up to y10. Now, this is a maximization problem. So, if you compare the values of the objective function for these 10 solutions, y1, y2, y3, y4, y6 up to y10, you'll find that y6 is a maximum, that is 25.04. Okay, 25.04 is the maximum out of these 10 y values. So, in this particular population, in this iteration, the base solution is your y6. Are you getting my point? And we'll have to find out its corresponding x. That means your x6 will have to mark. So x6, 0, 3.6 will have to mark, because this corresponds to the maximum value of y. Okay. Now let us assume C1 equals to C2 equals to 1 and W is equals to 1. Now the initial velocity of each particle, although it is very hypothetical, let me assume for simplicity of hand calculation, they are all put equals to 0. It's a very hypothetical situation. Now, P base to 1, 0. You see, initially we selected the values of x at random. So initially in the 0th iteration, what is P base? I am going to start my career this year. So what is my P base? This year's performance is my P base, personal best. Okay. So P base to 1, P base to 1 corresponding to 0 is minus 8.0. That is nothing but the value of x. If you see, this is the value of x. Minus 8.0, 7.5. Last is 6.7. Okay, this I am declaring that these are the personal best for 10 particles, 10 solutions. So P base to 1 corresponding to 0 is minus 8.0. P base 2 corresponding to 0 is 7.5. And P base corresponding to 10, 0 is nothing but 6.7. So I can find out this. Okay. Maximum of the personal best. What is the maximum of the personal best? If you remember, so y6 was the highest. You can see that y6, and its corresponding x is 3.6. Okay, so we are going to declare that global best is 3.6. Out of all the solutions, each solution is having its own personal best. Now we compare all the personal best values to find out the globally best. If there are 10 people working in the same field in the world, their performances are to be compared to declare who is the globally best. Okay. So G best with respect to 0 is 3.6. Let us consider the random numbers R1, 0, 0.2, R2, 0, 0.8. So the velocities, so this is actually R1 and this is R2. And C1, C2 and W, we have assumed those are equal to 1. Okay. Now how to update the velocity? So Vi corresponding to T plus 1 iteration is nothing but W multiplied Vi corresponding to T plus C1 R1 corresponding to T into P best I corresponding to T minus Xi corresponding to T plus C2 R2 corresponding to T multiplied by G base T minus Xit. So V11 is nothing but, so W multiplied by this velocity, initial velocity is assumed to be equal to 0. So it is 0 plus C1 is 1, R1 is 0.2. What is P best for the first particle? That is your minus 8.0. Okay. Minus Xit, that is your 8.0, because I'm concentrating on this. Just a minute. Yes, I'm concentrating on this minus 8.0. Okay. Next, I'll have to concentrate on the 7.5 P base 20. Yes. So P base I is minus 8.0, minus of minus 8.0 is plus 8.0. C2 is equals to 1, R2 is 0.8. What is globally based? 3.6 minus Xit is minus 8.0. And if you calculate, you'll be getting 9.28. So this is V1, that is the velocity of particle 1 in the second iteration. V21 is nothing but minus 3.12. Please calculate and check whether you are getting it or not. V31 is minus 1.92. Then V101 is minus 2.48. And once you've got the velocity, now you can find out the position. That is Xit plus 1, that is equals to Xit plus Vit plus 1. Okay. X1 with respect to 1 is nothing but X1 0 plus V1 with respect to 1. And if you substitute the values, you'll be getting X11 is 1.28, X21 is 4.38. Then comes your X341, X is 4.22. What does it mean? It means that this is the position of the particles, the 10 particles in the next iteration. So you follow that complete one iteration, follow the same principle for the next iteration, and through a large number of iterations, the PSA algorithm will be able to give you the best solution or the optimal solution. I hope the principle of PSO is clear to all of you. Now, before I stop today, I just want to tell you that we did not stop here. Okay, we did not stop here, and we could make further progress on this. And I'm just going to tell you the philosophy. How could we make further improvement on this? Okay. Now, as I told, that PSO has got some merit over genetic algorithm. That means here the particles have got some memory. Okay. But memory cannot be considered as an intelligence. Intelligence of a human being till today, although it could not be defined clearly. What do you mean by intelligence? How can you declare a particular person is more intelligent compared to another person? Till today, there is no concrete definition of the term intelligence. Okay, but the way we thought that intelligence have got many things, And as a result, a human being will be able to take the decision as the situation demands. So an intelligent human being will be able to take the decision as the situation demands. Are you getting my point? Now, if he wants to follow that or fulfill that particular criteria, my idea is only memory is not going to help you. Okay, so memory is considered as a subset of a big set of intelligence. Now, the big set of intelligence is a fuzzy set. Nobody knows its the boundary. Are you getting my point? And inside that particular, the big fuzzy set, okay, I've got a small subset which is nothing but memory. Memory, of course, helps to take the decision as the situation demands, but it is not 100%. Okay, what the PSO is having its memory. Okay, and people thought that memory means it has become intelligent. That is not good. That is not sufficient, in fact. So what you'll have to do, depending on the nature of the objective function, depending on the requirement at the different iterations, you'll have to take the decision. The algorithm will have to update so that it can keep a proper balance between population diversity and selection pressure. Keeping that particular philosophy in mind, we developed intelligent optimization tool like the Bonobo optimizer is one of them. Okay. I think Amit, are you online? Amit, are you online? Amit, are you online? Puspendra, are you online? Puspendra, are you online? Oh, I think both the TAs are not attending. But Amit actually in his PhD thesis has proposed and developed along with me that Bonobo optimizer. Okay. And already I have sent all the codes are available. Codes are available in my website. Okay. Papers have been published for single objective and multi-objective optimization. If you are really interested to use Bonobo optimizer, which could be even better compared to PSO, much better than genetic algorithm. Okay, so the codes are available in my website. That is that website, not our institute website. That is available in my another website. That is that Soft Computing Lab. That particular website. Okay, maintained by I think Gmail account. Okay, so there you'll be finding the codes developed by Amit along with us. Okay, so you can use those particular codes. Okay, and you'll be getting much better. And that particular optimization tool is an intelligent optimization tool. But don't think that there is no such further chance of improvement. There is a chance of further improvement. We are thinking to make it even more efficient. Okay, but as on today, might be that could be the best. Okay, so my request, if you want to use some sort of optimization in your PhD work, you can refer our code, you can refer our papers, and you can use it. Okay, we are still working. We'll be working on different research issues of this algorithm also, that Bonobo optimizer in future. Okay, and already people have started working. Even some researchers in abroad also, they have started using that algorithm. Okay, uh, uh, so I hope this particular algorithm and its modified version will be performing best, I should say, and you'll be able to get very efficient optimal solution using this intelligent optimization tool. Now, with this, I want to ask you if you have any doubt regarding this optimization tools. And as I told that this is not the end, there is chance of further improvement, okay, of this intelligent optimization tool also. And if you are willing to work in this particular field, you're very much welcome, okay, because there is a chance and it is a new algorithm. So I hope you'll be able to do very good using this particular the algorithm. Okay. Now with this, if you have any doubt, and you can ask me now. Yes, any doubt?
Hello, sir.
Tell me.
Uh, yes, sir.
Yes.
Sir, actually, there's an echo.
Tell me.
Yes, sir. I just had a small confusion that that in the slide 23, sir, if we take a look at the equation, the velocity
23.
updation equation.
Yes. Tell me.
Yes, sir. So if we are to consider the just the weighting, the inertia weight component, that the one that provides momentum, and if we are not to consider the cognitive and the social component, then this will just reduce to VID t plus 1 is equal to W VID, where W is the inertia weight.
Yes.
And that would be like, although this is velocity, but that would be like analogous to the SA, the uh, annealed, yes, sir,
Simulated.
simulated annealing.
Hmm.
So can we say that this the particle swarm algorithm is simulated annealing with the cognitive and the social component, like with the memory part?
You can say, but as I told, if you compare the performance for a complicated problem, PSO could be the best. Okay, but now our algorithm is the best, I should say. Okay, even much better than PSO. Okay, the Bonobo optimizer is the best as on today, according to me. Okay, but if you compare your this PSO with the simulated annealing, definitely PSO is better. Okay.
Yes, sir. Okay, sir. Thank you, sir.
But people made a mistake. People thought that PSO has got memory, so it is the best algorithm. But as I told, intelligence is something more than memory. Memory is only a small part of the intelligence. Okay, people thought memory, if a person has got very good memory, he is most intelligent. It's not like that. Are you getting my point? Memory, of course, helps, but memory is a subset of intelligence. Okay, that is actually what we are going to add in. We have added in Bonobo optimizer. Okay.
Yes, which means, sir, there will be another term which will be
No,
expressing the intelligence.
actually, if you compare this mathematical expression, we did not use in Bonobo optimizer. Their treatment is different. Okay, all philosophy has been kept, that memory, its ability to take the decision to adjust between your the balance between population diversity and selection pressure. It has got the restart strategy. Is very important. For example, during this COVID situation, ongoing COVID situation, what are we doing? What are we doing here? We are stopping and restarting, stopping and restarting. Okay. Bonobo optimizer had got that stopping and restarting strategy on. Okay. which is most important now. It has got that type of stopping and a restart strategy also. Okay.
Yes, sir. Yes, I'll. It seems actually interesting. I'll check
Just
it out. Yes, sir.
have a look. Have a look.
Yes, sir.
Okay. Okay. So any other thing? Any other thing? Okay, then let me stop here today. Okay. And tomorrow we are going to start at 12. Okay.